is using high-level synthesis could be, at least for the initial evaluation, could be also very benefit, right?
Right.
Yeah.
Absolutely.
Yeah. So do we have more questions? So otherwise, I'd like to thank you, Pravna.
Thank you.
For your time and attention. And we have now the third presentation.
Okay. Yeah, thank you, everyone. And for any further queries and discussion, please visit Circuit Sutra's exhibit booth in System C room in Lobby 1. We can catch up there. Thank you.
Thank you. Thank you. So our next talk will be about a single source system to register transfer level design methodology using high-level synthesis. This will be provided by Petri Solanti from Mentor. Petri, are you already in? I guess yes.
Okay, so now it looks like I got my microphone unmuted.
Yeah, thank you.
So, greetings from the beautiful Bavaria. I'm sitting here close to Munich, and my background is picture was taken for a couple of weeks ago nearby my place. So,
very nice landscape.
This is the place where DVCon usually takes place. So this has been very interesting session. Let me share my screen. Regarding the different design flows and experiments that have been presented here in this session, I'm having a slightly different approach, but all these other approaches, starting from Python, starting from from software code and going to the RTL, is also in my research area. So I'm working at Mentor Graphics as an application engineer for electronic system level design, and I'm also writing my PhD thesis in Tampere University in Finland. And my topic is electronic system level design flows, the analysis, and how to develop these flows. My co-author, Thomas Arndt, is an application engineering manager of Coseda Technologies with a long experience in System C and System C AMS. I've been working on the electronic system level since it was introduced in 2001 with a great hype and a lot of hope, but still today, 20 years later, design teams are using methodologies of 90s when building SoCs that are 1,000 times bigger than the ones back then. So typically, each design team is using the best tools and methodologies for their own design domain, which leads to usage of multiple different models in different modeling languages, resulting in a high synchronization effort and complex validation scenario. A new challenge is the growing demand for functional simulation models that customers can connect to their own system simulation environments. To overcome these problems, we need a new design methodology that minimizes the number of different models and modeling languages. The ultimate target is a single language design flow. Let's see if we can get there. This presentation gives first an overview of some problems of the traditional design flows. Then we specify some requirements for the language for multi-abstraction, multi-domain modeling, and introduce a single language design flow. And the flow is demonstrated using a small design example. A system-to-chip design process uses multiple abstraction levels, from mathematical algorithms down to transistor level for analog and gate level for digital. In many cases, the paper specification is the only common interface between the design parts and abstraction levels. Different modeling languages are used in the design parts and phases, make an automatic validation of the models very difficult. Too many times, the first functional validation of the system is the chip prototype testing. Creating a virtual platform models for software development or simulation IP for larger system simulations, for example in automotive or aerospace industry, is an additional effort to the product development itself. And one reason for the situation is the lack of a common modeling language. Requirements for a modeling language that can cover the whole range of modeling paradigms needed to describe an analog mixed signal SoC are demanding. It must support data types needed for analog modeling and digital hardware modeling and abstract data structures used in the software development. Polymorphism is required to prevent recoding of the model when moving between floating point and fixed point domains. Support for parallel processes and concept of time is needed when simulating parallel behaviors in the model. Compiler support enables reuse of the software parts for cross-compilation for embedded targets. Timing abstraction is bound to the model abstraction. Analog behaviors can be modeled with discrete time schedulers to a certain extent, but an accurate analog model requires continuous time scheduling. Untimed domain is needed for fast simulation and in the beginning of the modeling phase. For digital hardware, it is important to have a logic description that can be synthesized to a gate-level netlist for backend processing. So there are lots of requirements for the language that can be used as a single source modeling language for the full design process. Some of the most popular software development languages have libraries like Python, as was described earlier in this session, and tools to generate HDL description from the software code. Unfortunately, most of these tools are academic trials and they are not widely used in the production. Concept of time and analog signal modeling are supported only by hardware description languages System Verilog with an external package and System C. Both solutions are IEEE standards and used in the production. System C, which was originally developed to be a hardware description language with C syntax, is the most mature candidate for the single language design flow, and it also natively covers the software development. The core idea of the single source design flow is an abstract System C simulation model or executable specification that implements the whole functionality of the chip. The communication between the different domains enables modeling almost real operation of the system and full analysis of all parts of the design. The analysis information is fed back to the chip architecture planning, and hardware-software split can be optimized easily at this level. The executable specification can be refined further into the digital hardware and software implementation models with real communication interfaces and a reference model for analog design. The communication interfaces the communication interfaces between the digital and analog parts ensure a correct communication in the final implementation. Because the whole design is written in System C, which is principally C++, it is easy to wrap it into a TLM wrapper for virtual platform or external simulator interface for any kinds of co-simulation. Let's go through the different steps of the flow. Creating an executable specification is an iterative process. It starts from an abstract behavioral C++ or System C model that can be simulated and refined to fulfill the requirements. When the understanding of the design architecture grows, the module architecture is refined to analog, digital, and software partitions. The interfaces between the domains represent the later physical interfaces between the analog and digital hardware and software. Inside the top-level modules, the individual model hierarchies are developed further. Hardware-related performance bottlenecks can be analyzed in this level with help of the matchlib library, also mentioned in the previous presentation, which is available as an open source today. A graphical System C design platform with System C AMS support is a great help to design, maintain, and verify the integrity of the system model. Further development of the domains can now move towards the best modeling variant of the System C family: analog with System C AMS, digital in System C or C++, and software in plain C++. A comprehensive test bench is at least as important part of the design as the DUT itself. The test bench validates the executable specification against the requirements and paper specification and ensures that all corner cases are modeled correctly. Code and functional coverage analysis at System C level gives a good overview of the test bench quality. Because most of the design errors are introduced in the beginning of the design process, the verification should also begin here. Verification engineers can start to develop the test bench parallel to the model development. This provides also a second pair of eyes to interpret the paper documents. The model and test bench development are challenging each other. Test bench indicates missing or erroneous behaviors of the model, and code coverage analysis uncovers shortcomings of the test bench. When the model is refined towards an HLS implementation, the test bench must take into account the fixed point data type effects. Finally, the digital hardware part of the model is synthesized to RTL, and the System C test bench can be reused in the RTL verification. Some random tests are still needed to test HLS-generated logic, like reset behavior, bus interfaces, and the generated state machines. High-level synthesis requires a certain coding style to be able to generate efficient parallel hardware from C++ or System C. Typical coding style issues are dependencies between the loops that prevent unrolling them, multiple accesses to the same array in one loop iteration that cause multiple RAM accesses in one clock cycle, and module hierarchy problems that hamper the resource reuse and efficient scheduling of the hardware. Most of these issues can be detected in a very early phase by synthesizing the design with floating point variables before quantization phase. Focus of this test synthesis is the desired architecture and parallelism, not the area or speed. The test synthesis can be run even before the complete system is implemented by starting with smaller critical subsystems. It is usually easier to clean up the design in smaller units. Quantization is principally just defining the integer and fractional bits of the fixed point data types in the model. It is a well-studied area with lots of comprehensive academic studies. Yet, for the most projects, a simple methodology using value range analysis and simple log2-based arithmetic is good enough. Fine-tuning must be done with simulation anyway. Value range analysis should be done at every assignment inside the module and at the interconnects. The information needed is the maximum absolute value and the minimum non-zero absolute difference between two samples. The minimum difference indicates the value difference that must toggle a bit. Signedness must also be detected, but it is a straightforward operation. The extracted fixed point attributes are transferred to the fixed point type definitions, centralized into a single header file for small and mid-sized systems, or subsystem-specific files in large designs. This enables switching between floating point and fixed point domains without editing the functional code. When the design is quantized, we can explore the real hardware architectures. It is an iterative process trying different synthesis constraints, different module hierarchies, and sometimes also fine-tuning the System C code. Usually, the system architect knows what is his desired architecture and performance in terms of clock frequency and latency. This target is based on the experience from the previous projects or static analysis with Excel. Sometimes some other architecture might be a better choice. High-level synthesis allows the design team to explore different implementation options for the functionality quickly and reliably. Performance and area are two metrics delivered by the most HLS tools. Some tools can also provide power consumption numbers. When the optimal implementation is found, the synthesis constraints are stored into a Tcl script to freeze the implementation. The generated RTL is verified against the System C model using RTL co-simulation or formal C to RTL equivalence checking. If it passes the smoke test, it can be passed to the normal RTL verification flow with the System C test bench and coverage analysis data. Functional coverage data captured in the System C simulation covers only the System C code lines and functionalities that are described in the model. Behaviors generated by HLS, like reset behavior and generated state machines with resource sharing logic, must be verified by using random stimulus. The verification effort in RTL level is limited, but the verification architects are needed to define the verification strategy at the System C level. As an example design, we used a filter data path that removes a 50 Hz jammer and high frequency noise from a dual tone signal. The example design was developed by using COSIDE System C AMS graphical development and verification IDE. In addition to System C design entry and debugging environment, it provides also a rich set of System C AMS libraries and signal analysis capabilities. The initial model is implemented using functional library blocks for both data path and test bench. Both filters are abstract mathematical System C models. The only component related to the hardware implementation is the analog to digital conversion block that is needed to analyze the effects of the limited input accuracy to the filtering process. The ADC block does pseudo-quantization by converting the input signal to a fixed point data type given as a parameter and casting it back to double. This operation injects all quantization effects into the floating point signal. The test bench generates input signal with parameterizable signal levels. This allows testing the absolute limits of the algorithm to ensure that the design can fulfill the requirements. Algorithm performance is analyzed with frequency domain analysis using library components. Post-processing of the results can be scripted for automatic regression. When the functionality of the executable specification is correct and the test environment ready, the design can be partitioned into analog and digital modules. The analog part contains the anti-aliasing filter and AD converter. In addition to that, the digital part needs a clock and reset generator, which can be implemented on chip or externally. The digital part must be restructured to make it HLS compliant. High-performance mathematical models are usually optimized for configurability and simulation speed and do not have the clock and reset ports needed by a System C hardware model. Some HLS models can be found in open source repositories like hlslib.org or in the HLS examples delivered with the tool. In most cases, the algorithmic part of the mathematical model can be modified to include the reset and clock behaviors. The test bench can be completely reused, and the automated regressions work for the hardware implementation too. If the digital part is written by using synthesizable floating point data types, it can be synthesized to see if there are any coding style issues. Usually, the separation of the test bench and DUT and the separation between analog, digital, and software parts is expressed by a hierarchical structuring approach. But in this example, it is left flat to have the overview on one slide. The example design was quantized using a simple value range analysis method. The AD converter model in the signal part limits the possible value range and accuracy of the internal signals. The values are dumped with SC trace into a file during the simulation. From the trace files, we analyze the maximum absolute values and minimum non-zero absolute difference of the notch filter signals. The required number of integer and fractional bits can be calculated from these values using log2 function in Excel or Pocket Calculator, or by the tool via Python post-processing of the waveforms. The FIR filter can be analyzed statically based on the input and output data types and maximum possible value of the accumulator with the given coefficients. The data type definitions were collected into one header file. Now it is possible to switch the data types of the digital domain between floating point and fixed point and compare the results. The results can be compared visually using waveform viewer of the coside or by post-processing the simulation data and analyzing the differences with assert threshold. Both approaches have their pros and cons. The visual analysis reveals aspects that are difficult to detect with automated comparison. For example, the 50 Hz ripple in the difference between floating point and fixed point simulations indicates that the notch filter coefficients need more fractional bits. Automated threshold detection-based comparison is useful as a regression test once the design is fine-tuned. The example design was synthesized with Catapult HLS using different synthesis constraints to generate a minimum resource, long latency version, a medium-sized version using 4 multipliers in the FIR filter, and a fully parallel version with 2 cycles latency and throughput of 1. The notch filter is modeled as SE method that forces the synthesis to a single clock cycle fully parallel implementation. The FIR filter module is SE thread that allows the HLS tool to generate different implementations. The notch filter could also have been implemented as SE thread if multi-cycle implementation is needed. System C is the language that enables a single source language design from abstract behavioral description of an analog mixed signal system to RTL. A graphical System C design platform reduces the burden of writing the module architecture and connections, allowing the designer to focus on the behavior. High-level synthesis removes the need for RTL language and allows maintaining a high abstraction level throughout the whole digital hardware flow. With the presented methodology, only one model has to be developed and maintained. No validation between 2 different code bases is needed, and RTL verification environment can reuse the System C test bench. This methodology supports agile and traditional design processes, enabling efficient utilization of the resources. This flow was developed together with some design teams developing analog mixed signal chips. Some of them have published their results earlier in DVCon. This exercise was just a proof of concept. There is still a lot of work ahead of us, like testing the software interface and using matchlib for internal communications and verification. Thank you for your attention. Now it is time for the questions.
Many thanks, Petri, for your presentation. So we have time for questions. Petri, you can see also in the chat 2 questions from Jacob. The first one, I guess, is related to your slide 6, number 6, so where we have this table with also System C being used for different levels. So how you use the same language for all domains? Should it be better to raise the abstraction 1 level and generate a most suitable implementation language for each domain? System C is not very abstract compared to would be to a domain-specific high-level language.
This is a very good question. And the problem is that if we take very abstract level languages like Python or MATLAB, we can model fixed point algorithms there. And we can also generate C code or even RTL directly from this description. But if we use the higher abstraction level languages, we also need to write the hardware part in a very low abstraction level. And System C is one language that also can handle the software side, it can handle the analog side, not only the digital hardware. And that was the main reason why we chose System C as a modeling language for this approach.
And the second question is, when you add the high-level sentence details to your model, do you basically abandon the original model, or do you get back to this high-level model? So if you have any changes in the implementation. So usually you have, if you go back to the original model, so every time you have to to perform the high-level synthesis again. So if you have any optimizations in lower levels, so this is not considered anymore, or?
Yeah, there are two different approaches. So we can keep the abstract level reference model and compare the HLS implementation against that. Or we have a test bench that is checking the functionality of the System C digital model so that we are refining our original reference model, and test bench is detecting if there are some errors in that design. So our target was to get rid of the second reference model so that we have only one model that has to be maintained and developed further. It is also the question of the modeling abstraction on HLS level. So if we go to SE method-based modeling, then we must describe our hardware behavior very detailed and very low level. If we use SE thread and let the HLS tool to do the hard work, then we can write much higher abstraction level design so that we don't go down to the RTL level in our System C, but we remain in the behavioral level description.
But your intention is to focus more in a P design, not a whole SoC, right? So you're not intend to have a microcontroller and do the high-level synthesis for this microcontroller. So you replace by a macro later, right? Or do you intend also to perform high-level synthesis for the whole SoC, including microcontroller and so on?
Yes. So as I mentioned, this was a proof of concept, and there are already published examples of building a complete SoC using high-level synthesis. For example, NVIDIA has published one example of them. And we are really moving to the complete SoC implementation. It is not ready yet, but using, for example, MatchLib as a part of the design process. And we can take RISC-V model and synthesize that as a part of the design. And in that way, we can also assemble a complete SoC with high-level synthesis. Of course, the analog part is still, it must be modeled and developed manually because there is no high-level synthesis for analog designs.
Okay. Another question from Jacob. So concerning the virtual platform. So if you compare high-level synthesis models is about 1,000 times lower compared to transaction level in the virtual platform. So if you are working with the software development, so this is also a very important issue. If you have to run with the high-level synthesis models, not compared to the transaction level.
Yes, this is one of the future studies. The high-level synthesis model depends on many different aspects, and the simulation speed is influenced by the System C scheduler, which is one big influencer. And even a bigger problem is the SC data types. SC fixed data type simulates very slowly. And if we use, instead of SC data types for a virtual platform model, we can principally use double, because it doesn't change our behavior that much. Or we can take the AC data types, which are also in open source domain, which simulate much faster than the SC data types if we want to keep the fixed point arithmetics inside our TLM model. But principally, with this methodology that we have two different data types, we can switch between floating point and we can switch floating point and fixed point. We can create a TLM model using floating point variables, and then it also simulates very fast.
Okay. So do you have further questions?
Thanks, Jakob, for the very good questions.
And also thank you, Petri, for your presentation, and also thank you all for your attendance in this session. So now, then, if you don't have any other questions, I'd like to thank you all and also invite you for the DVCon virtual world in order to follow up for the discussions and then also continue with the next sessions in the afternoon. So thank you. And also you have additional questions, so also I guess you can also provide questions to Petri later. Thank you from our side. So have a good day. Bye-bye.